Good evening and welcome to the AES Melbourne and to a talk tonight by Paul Messick. Tonight's topic is low jitter clock generation for digital audio, something we all should worry about and master. The demands of modern audio converters make low jitter audio clocks a critical requirement if high performance is to be achieved. It is now possible to find affordable ADCs and DACs that approach or exceed 130 dB signal to noise ratio and minus 120 dB total harmonic distortion. Run-of-the-mill clock generators will not cut it for performance at this level. In this presentation, Paul will show how jitter affects audio, how much jitter is allowed given an audio quality target, and what kind of clock generators can achieve these specifications. He'll also talk about how to measure jitter. Since most pro audio systems need to interface to the outside world for timing, he will also talk about clock recovery and jitter attenuation. Finally, he'll tie all this together with measurements on a real product that achieves suitably stratospheric performance and possibly take questions. A little bit about Paul. Paul has spent more than 40 years, you don't look old enough, designing all sorts of electronics, everything from scientific instrumentation, radar and RF receivers, audio measurement systems and pro audio products, and a lot more that he's actually forgotten about by now. As a consultant or as an employee, he has worked for a wide range of companies around the world, including Dallas Semiconductor, JPL, Jet Propulsion Laboratories, M Audio, DigiDesign and more. He was head of engineering at M Audio DigiDesign and later founded Avometrics, which made production line and bench type top audio analyzers. Since moving to Australia, and we're glad you did, he has started Glassworks Audio, designing high performance studio gear for his own brand and for other select clients. I'd like you to welcome Paul this evening, and I'm sure you'll enjoy his talk.
Thank you.
Over to you.
Thank you. You want this?
Thank you.
Well, I hope I can live up to that introduction. We'll see. No promises. So before we get started, I wanted to set one guideline, which is if you have any questions, don't hold them till the end. Ask them whenever you have the question. The rule is there are no dumb questions or no stupid questions. There are only stupid answers. So with that, let's get started. Although Graham has introduced a lot of what I'm going to talk about, I'll go through it again a little bit just to bring us up to speed of what we're going to talk about, where we're going to go with this. So start with a quick refresher on sampling, just so we all see what it is that we're talking about. A discussion of the kinds of jitter and the effects of jitter on audio. How much jitter is okay for a given target. A few suitable clock generators that you might use. These include the sort of PLLs that you would use for clock recovery as well. Some ways to measure jitter. And we'll talk about a real design that I have in the works that I've done some measurements on, and talk about the limitations of making measurements. So let's start with Plato's ideal sine wave. This is the Platonic ideal. It has no noise, no distortion. It doesn't get better than this. And do some simple sampling here at some sample rate. So we'll pretend it's, say, 48 kilohertz. And each of those samples gets a value. That's our list of values that we can use to record and play back. But dark clouds over the horizon. Jitter. So jitter is moving the sample points back and forth randomly. And this is truly random jitter. This little plot here is approximately 30% jitter, which if you pretend this is a 48 kilohertz sampling, that's about 2 microseconds of RMS jitter, which will become clear what that number means in a little while, hopefully, if I do okay. So if we take that jittery sample and we've recorded those and we decide we're going to play this back, what might that look like? So that's literally as if it were played back with the sample playback in exactly the right place. And this is the effect of jitter. This is an extreme amount of jitter, which I had to do so you could actually see it, because basically at low levels you can't see it in a waveform, and it's actually becomes quite hard to measure. So there's a couple of things we can notice about this. One is that there's not a lot of cycles here, but you can make the observation that it's not harmonic distortion that we're seeing. The distortion is almost entirely just added noise. This noise is, for our purposes, we're going to stick with noise that is Gaussian. In other words, it's flat white noise. The same amount of noise for all frequencies, which is what this plot would show. And that's typically approximately correct. So given that jitter, the effect of that jitter, what are the different kinds of jitter? And jitter is a bit like the joke of standards. You know, standards are great because there are so many of them to choose from. So this is also true with jitter. There are lots of different kinds of jitter. A lot of them are related to timing margin on digital signals. So setup and hold times. Not entirely what we're interested in with sampling. We're interested in the sample points being in the right place, not so much that there's some digital signal that needs to be ready in time for another clock, that kind of thing. So typical types that you'll see: period jitter, cycle to cycle, long-term jitter, time interval error. Everybody seems to have one. They're all very similar. They're all, a lot of them are variations on how you measure it or what it's referenced against. So the one that is pretty typical that you see is period jitter, which is a deviation in time from either an ideal or, in the real world, from an average frequency. So if you think of signal going along, samples happening, a perfect sample rate is 48 kilohertz, so every 1/48 kilohertz, there's a new sample, and the jitter is the variation, the period jitter is the variation over these periods of when that occurs. Another kind related to period, well, one of the ways the jitters related to period is peak to peak. That's very interesting for things like PLLs, because if the jitter is too much, the PLL may lose, on its input, it may lose lock, for example. But that's not really what we're talking about here for audio. The more important jitter is RMS, which is, if you're talking about this in terms of statistics, it's a standard deviation, but we always refer to it as RMS. And you can get the peak-to-peak jitter from the RMS, at least an approximation, with this little formula here. So it's useful to understand what that is. For audio, though, the most useful is RMS, because we're talking about basically noise, and that noise is, as I said, flat white Gaussian noise. And RMS is a good measurement for that. And a thing that's worth noting is that when you're measuring jitter with an RMS measurement, it's measured over some bandwidth. So a typical bandwidth would be 100 hertz to 400 kilohertz, where it's the audio passband up to twice the sampling frequency. And I'll talk a little bit later about why you would pick those numbers. You'll find data sheets that use different numbers. You can make your jitter look better on paper by picking a different bandwidth, but this is one that gives you a pretty good idea of what your system's doing. So we assume that the jitter is random, it's noise, and that noise follows this curve. So the signal to noise in the system is a factor of the jitter in terms of time, T sub j, and the frequency that you're interested in where the SNR is measured. I can make this a little more clear by showing you a curve of what that looks like. So this red line here is this formula, where as frequency goes up, it's going up at 20 dB per decade. If here's a plot of what the SNR would be for a codec with a 130 dB SNR, and if we assume that we've got a clock with 20 picoseconds of jitter, this is what will happen to it. The noise floor starts out at 130 and it looks great until here a fairly low frequency. This is in the audio passband. It starts to rise, and it rises at 20 dB per decade. And by the time you're at fairly high frequency, your nice DAC or ADC isn't that good anymore. That's a not great result. So how much jitter is okay? So you have to pick some frequency where you decide that you want to keep the jitter low below. If you picked a 1 kilohertz, your result might not be so great. So I'm arbitrarily picking 15 kilohertz. Your mileage may vary, but it's a good place, I think, to start. So we do a little bit of math on that formula from before, and we get this number. And so at 15 kilohertz for 130 dB SNR, which is our target, the jitter needs to be 3.3 picoseconds. If you remember that jitter that we had on the sampling slide, that was 2 microseconds. So 1,000,000 times more, basically, before you could see it. Gives you an idea of how low this jitter needs to be. And here you can see what the curve did when I used this new clock that has 3.3 picosecond jitter. It only starts to rise just a little bit above 15 kilohertz. That's certainly much better. And now we're getting our 130 dB data sheet spec on our nice codec. A much better result. So I should have had a slide here about, well, I will in a second, about exactly where jitter comes from. But we're going to talk about, for a second, oscillators, which is how we get these clocks, so our sampling clock and so on for audio. So what makes a good oscillator? You want a high Q, which is, Q is literally the carrier frequency divided by the bandwidth. So if it's a very narrow bandwidth filter, you get a very high Q. And if it's not a very good bandwidth, quite wide bandwidth, you get a low Q. So you want it as high as possible because it filters out the noise that's inherent in the oscillator, and you get less jitter because it's being filtered. So that gives you what we refer to as low phase noise. And this is a plot. I don't know if you can see it very well. Yeah, it's not very good up on the screen, but you can see it starts out on this graph at 1 hertz, and it's going up to, I don't remember what this one goes to, a couple of megahertz, I think. And so you can see there's a typical curve here of it rises pretty rapidly as it goes towards low frequency, and then there's a flat section, and then it falls off. This is very common. So you want your oscillator also to be high accuracy, not have a lot of drift, not drift with age. So crystals are the gold standard. If you have a crystal oscillator, it's going to meet these criteria very well. And this curve is, in fact, for a crystal oscillator, similar to one that I use, and you'll see more data on later. But they have the problem of they're fixed. Just fine if you're the clock generator, but if you're trying to sync to something external, they don't work quite as well for that. So VCOs come in, and very common to use PLLs to recover clocks. Like, for example, if you have system word clock, you're in your studio and you plug in word clock, now there's a PLL that's going to sync to that to generate all your internal clocks. So VCOs take multiple ways of doing it, but I'm going to talk about 2 different kinds. LC oscillators, which is the old standard RF. There's an inductor and a capacitor, and they make a tuned circuit. They have a pretty high Q, so they tend to have pretty good phase noise, low jitter, in other words. But they're expensive, they're big, they usually draw a lot of power, they're sine wave outputs, so you may have to do some extra finagling to get it into the digital domain. So they may not be ideal. They're certainly not cheap. And they have a moderate range. They could tune, most will do 2 to 1, in other words, from its lowest frequency to its highest. It's possible to get them pushed up to 10 to 1. Those might not be very good in terms of phase noise, but it's a moderate sort of tuning range. The other kind that you see that's very common is called a ring oscillator, which I'll go into in a bit more detail. It's characterized by really low Q. The Q is typically a 1 or even less. So they really are lousy for phase noise. And they're very, very cheap. There are literally just a few inverters in series. When I say it's a ring, it's literally a ring, and I'll show you that in a second. And they can be tuned over a very wide range, easily 10 to 1, often quite a lot more than that. So the ring oscillator, here's a little ring, and it's an inverter that drives another inverter, that drives another inverter, and so on around, like an Ouroboros. And so when one of them transitions for whatever reason from a 0 on the input to a 1 on the input, then you get a 0, then you get a 1, then you get a 0. And now that feeds around, and it goes around and around like a ring. And you can tap off of one of them, and there's your output, and it's a nice clock. But they have, as I said, very poor phase noise because they have no cue. There's nothing filtering this. It's just literally noise going in a loop. Very easy to adjust this frequency for the oscillator because all you have to do is change the gate delay, which you can easily do with some voltages. You literally just vary the power supply voltage, and you can tune it over a very wide range. But the jitter is pretty lousy. Easily it exceeds a nanosecond. When, remember, we're looking for some number that's in the low picosecond range. Here we are at 1,000 times that. So it seems kind of hopeless. But if you set the frequency of this thing very, very high, this is well above your microwave oven here, and you divide it by a large number, then the jitter is divided just like the frequency is, and actually quite easy to get less than 100 femtosecond jitter out of an oscillator like that. So you start with something that's really pretty poor and crank it up to a few gigahertz and divide it down, and you get a pretty clean clock. There is a limit, because otherwise you'd say, why don't we just keep going higher and higher and make it more perfect and more perfect? And there is some of that goes on out there, but there is a limit because dividers also add noise every time you run another stage of a divider. It has some noise of its own, and so you reach sort of an impasse. So all of this is building up to being able to take an input signal that may be jittery and get yourself nice, clean sampling clocks so that your very expensive 130 dB SNR codec works properly. So examples: word clock, AES inputs, media clocks from various sorts of networked and other sorts of sources, syncing to video and so on. These are all sources of what would very commonly be jittery clocks. Some of them are extremely jittery. If you're back in the day, you might actually try to sync to film from the sprockets. And you can imagine how bad that is, but you can clean it up. So we need to generate audio clocks, and I'll mention in a minute which ones we need, but you need audio clocks so you can run your ADCs and your DACs so that they're sunk to whatever your external time base is. Oh, well, I did mention it right here. So you need the LR clock, which is left-right clock. It's sometimes called frame sync, word clock. Just like standards and jitters, everybody's got a name for their own version. You have a bit clock, which clocks the digital bits in your stream. And you have what is commonly called M clock, which is the one that really needs to be clean, because that's what drives the sampling part of an ADC or a DAC. One little extra thing you need to keep in mind is that LR clock that you're using internally has to stay synchronous to the LR clock from your outside sync source. Because otherwise your samples now are no longer lined up properly and you get garbage. Usually this is done with a PLL. And you'd think, I run my word clock into a PLL, multiply it up, and I get my M clock, and everything's great. It's not quite that easy, of course, because LR clock, as I said, has to be synchronized to the frame sync. This makes things a little bit more difficult. And noise from your input can pass through the loop without being attenuated at all if that noise is inside the loop bandwidth. So these are little complications that you have to try and deal with. Since I keep mentioning PLLs, maybe I should define it. Might be handy. So everybody's seen, oh yeah, it's not too bad. The little loop that is a PLL. There's a phase frequency detector. You have a loop filter. You have a VCO and a divider. So if we're running 48 kilohertz in, if FREF is 48 kilohertz, and we want M clock to be 1024 times that, which is 24.576 megahertz. These are very typical audio clock frequencies. Then N is 1024, and you multiply up that 48K up to the M clock frequency. So you have a pretty narrow loop filter here, hopefully. But anything inside the loop bandwidth, so any noise that's coming in to your from your external clock source, is going to pass right through, and in fact it gets multiplied up by n. So here it's 1024 times more. That's great. Didn't help very much. And you still need to do the dividers to get your bit clock and LR clock, all those other audio clocks, which are all fixed multiples or divisions of the M clock. So there's a way to actually make this problem mostly go away, which is called the hybrid digital analog PLL. So it looks a little bit like this. This is a very simplified block diagram. So we've got our reference input here. We have a thing called a digital PLL, followed by an analog PLL. And we're going to then divide that down, and that is our loop. And out of that, theoretically, we should get some very nice clean clocks. So the digital PLL has very low bandwidth, very narrow bandwidth. Very typical is 3 hertz, 1 hertz, very, very narrow filter. So it still has the characteristic that any noise that's coming in will pass through that loop filter. But if the bandwidth is 1 or 3 hertz or 10 hertz or something like that, it's not very much noise. And it also does noise shaping, which will push any noise that is coming in up in frequency. You can push it quite high in frequency. And then, I don't show it here, but the output of that digital PLL actually has a little low-pass filter there. So if you push your noise up in frequency and you low pass filter that, now that noise is gone. So we push it up, it doesn't go through that low pass filter. Now that this analog PLL is driven by this now very clean intermediate digital signal. So, yeah. So we've effectively gotten rid of the jitter this way. And there are a number of ICs you can get that are out there to do this. A lot of them are, as I dug around to find new ones, there are a lot of them that are actually made for telecom, not really meant for audio, but some of them you can actually squeeze a bit and get them to work okay for audio. And I'm going to talk in some detail about one of them that I use quite a bit. But there are some others that I'll mention. So these typically have multiple inputs, so you can select different sources. They have multiple output frequencies, so you can get all your different audio clocks out of one chip. Some of them have multiple PLLs that are completely independent, and that can do some interesting things that you might need. A few examples. So the granddaddy of these is the Jet PLL. So this is Chris Travis's invention. That they're all audio-centric. It's an FPGA solution, either using a ring oscillator or an LC oscillator. They're external, and you can get jitters in the 10 to 25 picosecond range, typically. These tend to run with clocks running in the 50 megahertz or maybe 100 megahertz kind of range. That 7200, which is a relatively new part, which is based on the Jet PLL. It's licensed by that corporation to do that, and it's, at least on the data sheet, 25 picosecond. It's kind of typical number. Cirrus 2600. Which is fairly popular. That's also a Jet PLL. I don't know if it's a licensee. I think it is, but I don't want to be quoted. So its data sheet is anyway 18 to 25 picosecond kind of jitter. Then we get into some of the telecom parts. So there's a microchip, which used to be microsemi. That was made for telecom, and it's in the range of 200 femtoseconds. In some modes, it might even be less. Renesas has one that's relatively new, a little bit better. Jitter, I haven't used it, so I'm not exactly sure how that works out, but it looks like it's a very similar kind of a part. Skyworks, which is also very popular, you see quite a bit. They're actually a telecom company, but they sell quite a bit into the audio world. Their parts are running 100 femtosecond sort of range. So these are all very, very good for jitter. But I've done a lot of work with the 3252. And so I know it very well, and it has some very nice characteristics. So this is a more expanded block diagram of what I showed before. It has some various inputs, 3 in this case, a digital PLL, followed by the analog PLL. And then the outputs are a set of dividers that can get all kinds of division all at the same time. So it can run as many as 6 different frequencies, all some multiple of a base frequency out of there. And so the digital PLL here is running in the 700-800 megahertz range. It could be a little higher and a little lower, but that's a typical number. The analog PLL is running quite a bit higher, 3 to 4 gigahertz. So the designs that I'm doing run in 3.75 to 3.9 gigahertz, and that gets divided down to, so this is how we get this nice low jitter. Yeah, we have, as I said, multiple inputs, 6 outputs. All these outputs can be adjusted in phase as you may need, so that's kind of slick. And you remember the constraint that the output LR clock needs to match the input LR clock in terms of phase. And that can be tricky to do. So in this case, the way you do it is you feed the output back into one of the inputs and tell it, do your magic. And it will synchronize so that the input and outputs are always time aligned. Jitter on this, running things to get an output at 24,576. Typical sort of number would be about 1 picosecond, 1 to 2 picosecond sort of range. So those are all nice. That's all good theory. But how do we actually measure this stuff? With all things jitter, there are many ways to do this. We're interested mostly in the RMS. There's a whole set of ways to measure and gear to measure jitter that is the peak-to-peak kind, where you're interested in setup and hold times and so on. But we're really only interested in RMS for the audio world. And so there's a few ways that are common. One of them is an RF spectrum analyzer and some software, which is a method that I'm using, and I'll show you exactly what that is in a minute. A lot of the equipment you can buy off the shelf does something along the lines of down convert from a higher frequency to a baseband and then do some analysis of various kinds there. One of the ways that that's done is a quadrature detector. Basically, you have a mixer, you have an input, and you have the same input shifted by 90 degrees. And the output of the mixer will be a DC signal that is the phase difference between those two, which sounds exactly like what we want to do to measure jitter. There are various ways to get that quadrature. You can do it with a PLL, which has its own issues. You can do it with a delay line, and so on. Those tend to be narrow band, single frequency, unless it's a PLL, but it's a very effective way of doing it. There's a piece of gear I've seen out there that does a very clever thing where it has one input that gets multed to 2 and measured in 2 systems, which it then does a correlation, cross correlation on it, so that the any noise inside this device, for example, its internal oscillators, cancels out. So you get rid of that would be the common mode, and you end up with just the jitter measurement of your input. Actually, quite effective. And then there's another one that's a purely digital way of doing it called a time-to-digital converter, which essentially just measures the amount of time it takes for a clock to propagate. And You measure that over and over and over again. You run that through an FFT, and you do a little bit of math to it, and you can get jitter measurements that way, which is a very interesting way of doing it. Something worth exploring more thoroughly someday, maybe. So what do you do with these measurements? So if we're doing this with a spectrum analyzer, say, or this TDC methodology where you have a frequency plot and you want to know what's the RMS jitter that goes with that. RMS, and I'm going to put you all to sleep here. RMS jitter is the integral of the phase noise over some frequency range. And already I can hear the snoring. Another way of referring to it is it's just the area under the curve, which makes a lot more sense. So here's that oscillator that we saw much earlier on. This is off its data sheet. I've munged this a little bit because that's a 100 megahertz oscillator, and I want to know what it's like at 24,576. So I have mapped it down in frequency. So this is actually this data is has been translated to 24,576. And here we can see what the area is under each of these main areas. So as you go down in frequency, that it goes up quite rapidly, but that's a very narrow band. That's from 1 hertz to 10 hertz. That's a 9 hertz bandwidth there. From 10 hertz to 100, is that, I can't really see it. From 10 to 100, and then from 100 to 1 kilohertz, so that's definitely in the audio band. It's starting to come down, but that's where, if you look here, that's where most of the jitter is coming from. It then flattens out. So you get another decade worth, but it's much lower. And we don't go quite a decade out because we're going to cut things off at 400 kilohertz. So here are the three parts that are added to it. We get 700 and something femtoseconds, right? Yeah, 727 femtoseconds of jitter from this oscillator. So it's pretty good. This is a typical way of doing this. So they'll measure this phase noise, which is literally just the plot of what the oscillator is doing at a single frequency as it rolls off. It's the noise out of the oscillator, and they do this math to it, and very common to do. There are a number of instruments that you can buy if you want to just do this. A few examples. There are a couple of things from Rode and Schwartz. There's a very nice phase noise analyzer. I think one that's fully maxed out is about $300,000 US. So good luck with that. Is a very common one is the Keysight signal source analyzer. There's also an Anritsu box that is very nice. Interestingly, some of the oscilloscopes that are out there can do this. Now, these are not the ones that you're going to get off of Alibaba. They are, well, let me get down to these things. All of these instruments here are 100K and up. So maybe not something, unless somebody gives me one, I'm going to have. So how do you do this? Well, I've been doing some of these measurements for quite a while, and I've come up with a kind of a homebrew way of doing it. It's no longer great. It used to work quite well, and I'll tell you why. So I use a spectrum analyzer. It's got a nice low noise local oscillator, and I use a little bit of software. So in my case, I've got a older HP 8566, and John Miles has a phase noise program, which he gives away for free, which is really awesome. A very nice program. And the 8566 is pretty old. I think mine is a 90s. It's one of the last ones, but they date back quite a long way. They're aging. In my case, as you'll see in a minute, the jitter of its local oscillator is actually been getting worse with time, and it's not that great. But it's all I can afford. They used to be, this slide until this afternoon said readily available, but then I went and looked at eBay, and I have to say, it used to be readily available for pretty cheap. Not so much anymore, but you can look around, you can get and it might be that some of the newer spectrum analyzers you can get for not a lot of money might work okay for this. I haven't tried one. I don't know what their close-in noise really looks like. Lowest jitter that I managed to achieve is in the 8 to 10 picosecond range. Used to be pretty good for what I was doing, but now the demands are quite a bit higher, so I'm not sure what to do. But John's software is free. It has a lot of features. It works with a lot of different analyzers, so it's a good place to actually start and experiment with this. So here's the board that we're talking about. And you can see there's a lot of chips on here. There's an ARM, which is the big one there. There's a power supply here over on the right. In the middle is your obvious USB interface. And on the upper left-hand corner is the chip, which is the ZL3252. And that's really all it takes. And below it, you can see there's a crystal oscillator. It's a TCXO with very nice specs and not very expensive. So this board has internal sync, it has external word clock sync, it has various kinds of media sync inputs. So it's intended to be used with some hardware that could provide various sources of sync. There's the TCXO. It outputs whatever the frame sync is, 64 times that, which is your bit clock, and M clock, which is, if you're in 48, 96, 192, is 24576 megahertz. And it does all the standard audio sample rates. That chip, one of the cool things about it is it's really pretty cheap. It's $11 in low volume, and it basically takes care of the problem for you. So here's my little test setup. There's the gigantic 8566 there in the middle. In this setup, I have a GPS discipline oscillator that I use for these kind of measurements. It actually turns out to be not that helpful anymore. It has the characteristic of being very, very low jitter. It's a very clean oscillator source to drive the time base for the instrument. But as I point out, the instrument's not doing so well anymore, so I didn't really need to drag out the GPSDO and spend 2 days getting it to find the satellites and all of that. You drive it with, in my case, a Prologix GPIB to USB adapter, which is a very inexpensive, very nicely made little interface. Drive it into my laptop or what have you, and you just drive your device under test into the input. And that's the setup. So, looking at the measurement, it looks like this. So I'm measuring this in the 100 hertz. You'll see there's a little blue line. Well, it's all the way over on the left, so you can only see the 100 there. And 400 kilohertz. And measuring that oscillator, this is just set to internal sync. We get 9.3 picoseconds, which is not bad. But we're just measuring the instrument at this point. And I know this because the 252, just based on the data sheet, at 24,576 should be in the 1 to 2 picosecond range. So we're measuring something way below the noise floor of the instrument. So you got to ask yourself, why are you doing this? Which is an excellent question. But assuming, let's just say it's the worst case of that, so at 2 picoseconds, the signal to noise at 15 kilohertz would be 134 dB. Our ADC or DAC is spec'd at 130, so we're doing better than that, and that should work pretty well. Anybody got any spare money, or maybe a lotto ticket? So the conclusion is very low jitter has actually become pretty easy to generate. You used to have to go buy some pretty exotic gear. It's quite expensive to do this. Studios, and still do, I'm sure, have something in the rack that would generate this, but it's not trivial, and it's not no cost, but it's low cost and not that hard to get quite good jitter now. Measuring it's not so easy, at least cheaply, short of a lotto ticket. But good to have a good spectrum analyzer around, because you can look for all kinds of noises, spurs, narrowband stuff. I've spent an unbelievable amount of my time chasing little birdies around to find out where they're from and escort them out. Because that's, until you get those clocks clean, you don't know what you have with your audio. Any questions? Sure, there must be. Anybody who's still awake.
Feel for what kind of jitter we can expect in a studio environment, for instance?
Well, it's the individual gear typically. Even if you have, say, a distributed word clock that's very low jitter, you have to expect that the devices that are connected to that word clock are going to be doing the right thing, and that their jitter, their clock regen is going to be low jitter as well. I would say gear up to present day minus maybe a few years has typically been jitter in the 10 picosecond range, which is not a terrible thing because the kind of converters that you might have would be performance that would match that. So if you have a let there be light. If you have an SNR of 120, 125 dB, something like that, then 10 picoseconds is not a terrible match. 125, that might be too hard, but 120, because not uncommon to find converters that are in studio gear that are 115 to 120 dB SNR. Now you're seeing some converters that have 130 or even more SNR, and this starts to become much more critical. There's not probably a lot of gear with those sort of performance parts in them, but it's non-zero, and so I think you'll see over the coming years some shifts in that direction. Yeah.
Hey, Flo.
Hey, Luke.
Again, most of this is way above my pay grade, but I've noticed when looking at network clock recovery, if I look at just word clock out of my master clock in the scope and what I've recovered over AVB, weirdly Dante hasn't been so bad, so it might be my terrible code, but that it wanders around a bit. There's a point where it's perfectly in sync, and then it's kind of a bit loosey-goosey for some number of frames until it's so it never drifts so far that it can't recover, that the FIFO fills up or is starved, but it's not in sync with the word clock that I'm feeding from my master clock generator. What are the audible artifacts of wander? I mean, I could also ask what to do about it, but it's probably a coding thing. But is it worse than jitter? Should we be more worried or less worried?
Perhaps less worried in that particular instance, because that's not entirely jitter. Okay. So one of the things that you have with a network system is there's a bit of a, how do we term it? It's not as tightly bound because of all of the slack that's in that whole thread. You've got there's quite a bit of distance, and these systems are not phase locking. They're doing what a GPS DO does, is they're disciplining the oscillator. Now, because they're a network is a pretty jittery thing to begin with, the disciplining isn't very tight. So that's why you see this wander back and forth. They're pushing it back and forth.
The recovered clock from the Brooklyn is actually pretty good wander-wise. Sometimes, depending on when I restart it, it's not always great, but it's pretty close. Whereas the AVB one's pretty all over the place.
They're all doing it to a greater or lesser extent. Yeah. I don't do anything with AVB, but I do. I mean,
it should be better in theory. That's what the pundits say, but it could be an implementation issue.
That could be a lot of different things, but the wander is not. That's not that worrisome. What does happen is that if the wander is not carefully driven, if you get any jumps, then you have that will translate directly into jitter. Yes, and the recovery from networking, as I understand it, and this is getting a little outside of my wheelhouse, is that it's the individual packets are pretty jittery.
Yes. Yeah.
So there is quite a lot of of jitter there, and you have
But
to
you
work.
expect that because that's
You
that's
expect
way of
that.
a buffer, right?
Right, and that's what parts like this can do. So if you take the output LR clock out of one of those systems and feed it through a jitter attenuator, then you're going to end up with your M clocks downstream being much cleaner than if you just took the M clock that was being shoved around back and forth by the network.
Yeah.
So those are two little bit different things.
Yeah.
Both of them kind of from the same problem, but one of them's over a longer time frame and one's over
And
a very
how would it manifest in the audio domain?
The wander shouldn't, because unless you run out of samples somewhere,
Okay, and
you shouldn't.
remind me, I think I vaguely know the answer, but the trade-offs with the loop bandwidth. Is
Well, the narrower the loop bandwidth, the less noise,
yeah,
but the longer it takes to lock.
right, gotcha.
So if you have your 1 hertz loop bandwidth and it was just fixed at 1 hertz, it could take it seconds or tens of seconds to lock,
Which is
depending on
why I
how
suggested
unlucky.
you start with a high one and then you once
so
you're locked, you change.
The usual trick is you set these up so that they're running as wide a bandwidth as they can. When they get locked, then you set that loop bandwidth back down again. As soon as it unlocks, you go back to the wide bandwidth. So that's a very, very common technique, because otherwise you'll sit there and wait for it to lock and lose your patience.
Thanks very much. Have we got any online questions?
Did we-
I don't know.
We may not. Well, your audio, and you thought it was safe. 24 kilohertz, maybe 48,
Yeah.
96, 192. We've gone right past megahertz up to gigahertz, 4 gigahertz if you want quality audio. So now that you all understand the challenges that you are facing, you can certainly concentrate on what Paul's been saying. Are there any other questions?
There's none online either.
Okay, well, I certainly want to thank Paul for a very informative talk, which has cleared a lot of things up, probably horrified a few people.
Yeah,
But I do
and put a
thank
few
you
to sleep.
for your session. And as part of that, I'd like to present you with a small token
Well, thank you.
of
I'm sure I can find a
thanks.
use for this.
Yes, and it's yours. Don't let me or Peter get at it, okay?
No, especially
And
not Peter.
So I'd certainly like to thank you, and if you can just give us a bit of a round of applause for Thank you very much. That's excellent.
Thank you.
And there'll probably be discussion afterwards, but I thank the online people for being involved, and we'll have a bit of a chat, but I'll close the meeting now for AES Melbourne. Thank you.